The Beowulf disruption, changing the course of HPC.
Numbers touch us every day. Weather forecasts, cell phones, pharmaceuticals, gasoline, and even potato chips have been developed by manipulating numbers. Lots of numbers. Science, technology, and engineering are based on creating mathematical models and designs that need to be solved on a computer. These models provide insight into our world and answers to the questions that would be physically impossible to answer without computers. Traditionally, these computers were called supercomputers, and due to their cost, were available only to a select few. Today, this level of technical computing is called high-performance computing, or HPC, and is available to almost everyone. How did a once elite class of computers give way to a more open and economical approach to technical computing? This brief video describes the incredible story of those individuals and communities that pioneered a cheaper, better, faster way to deliver HPC to scientists and engineers. As mentioned, the initial cost to enter the supercomputing club was rather high because each vendor created its own processors, storage systems, and software tools. In many cases, a supercomputer used a handful of speedy custom processing units that were far faster at numerical computation than business computers or mainframes. There were some limits, however. The cost of fabricating faster processors increased considerably and gave way to utilizing multiple slower but mass-produced processors designed for Unix workstations. In addition, the speed at which a processor could perform had an upper limit. As problems grew larger, the need for faster solutions ushered in parallel computing, whereby a single problem was distributed across many processing units. HPC problems are some of the largest there are, so adding more processors, workers, was a natural way to achieve the required increase in performance. In many cases, this approach can scale up as the size of the problem grows. Two main hardware components were needed for scalable parallel computing solutions: processors with local memory and a communications network. In terms of software, an underlying operating system was needed, along with the programming libraries that would allow communication between processors. Previously, building a parallel computer required expensive, high-end components. A funny thing was happening at the low end, however. Mass-produced commodity parts were improving year over year due to the growth of the Windows desktop and then server markets. As these low-cost parts continued to improve, the idea of a homegrown parallel computer started to take shape. Some pieces of the puzzle were still missing, and there also needed to be someone willing to take a risk and try the idea on a real problem. The Beowulf project was born from such a need. Thomas Sterling and Don Becker, while working at NASA in the early 1990s, convinced Jim Fisher to fund the first Beowulf system, an open-source Linux-based HPC clustered system. Jim's vision, foresight, and courage to stand up to his boss created the space for the Beowulf project to succeed. In addition, early Beowulf pioneer John Salmon worked for Paul Messina, who ran the Center for Advanced Computing Research at Caltech. With Messina's support, Sterling was given the time and space to continue his Beowulf work. What actually got the Beowulf project started?
It was one of those unique moments that got the Beowulf project started. Suddenly all came together. In my head, I wrote a memo to Jim Fisher, and I laid out in less than a page the story, and he said yes, and that's how history was made.
Why is it named Beowulf?
One of Jim's very capable administrators called me and said, I need the name of the project immediately. I said, I'll call you back. She said, no, it's either now or we name it ourselves. I just looked around and then saw an old copy of my mother's college-bound version of Beowulf. I said, oh hell, just call it Beowulf. Nobody will ever hear of it anyway.
Were you ever told it would not work?
For the first 3 years, we were not only told it wasn't going to work, it was emphasized that it couldn't work. And even if we could do it, it would be disruptive to the entire field of supercomputing.
Did you think it would ever get as big as it did?
No, we did not think it was going to be big. That was never the goal. The Beowulf project was a project to test on hypothesis, a possible concept of achieving cost-effective computing more than a factor of 10 over what contemporary commercial systems were doing at that time.
What pieces were missing when you started the Beowulf project?
We initially thought the missing pieces were key technical elements. In the end, it wasn't the technical contributions, but building the infrastructure, helping people collaborate, bringing together the community that made the project a success.
Why not just use Windows?
Around 1996, people started asking us why we weren't switching to Windows. We knew that it didn't have the detailed technical capabilities we needed, but we also knew that we built a community around open source, and that was a key element of what we were doing. It turned out to be the right choice, both technically and for the community.
What role did open source play in the project?
We were lucky enough to have the Linux kernel as an example to use. That was a brand new concept, people working all over the world, and we wanted to draw some of that into the high-performance computing world, which was always site-specific professionals working on it. We wanted to build that same kind of community. It didn't translate exactly, but we succeeded in bringing people together to work collaboratively on building scalable cluster computing. It was a community that allowed us to do something much larger than we could possibly hope to accomplish at a single site. We were putting together projects from all over the world. All the people in the Beowulf project changed the way computing was done. It was only the collaboration we had of people at the different national labs changed the way computing was done.
What motivated you to take a risk on this new idea?
Goddard had been experimenting with massively parallel computing for a decade. Back in the 80s, we hosted the massively parallel processor at Goddard, and it was very expensive, and the amount of software that was developed for it was very small, because it was only one of a kind. And so it was motivating me how to develop software for these highly parallel systems. And when John Dorband and Thomas Sterling came into my office with this PC Linux cluster idea, my first reaction to that was, it's going to be incredibly inexpensive. Plus, I was already trying to build this kind of a thing, so I had a budget for it. And so I said, great, go ahead.
In your opinion, did the project meet your expectations?
All I was hoping to get was a gigaflop workstation to support some of the science users at Goddard. Linux cluster systems kept getting bigger, and the price was competitive. It was very competitive. And one of the biggest computational challenges that Goddard had for years was data assimilation. It was the Linux cluster that stepped up to that. That is exceeding my expectations.
What was the goal of building out open infrastructure application software for the Beowulf clusters?
Well, MPICH contributed to the project because it provided an open source way for people to program the sort of distributed memory parallel computers that the Beowulf project provided. Beowulf created a whole community of programmers, developers, and users of the sort of parallel computing that MPICH enables.
How was the genesis of OpenMPI guided or influenced by the Beowulf project?
The four MPIs that directly preceded OpenMPI and were the basis for OpenMPI, those were all much more directly impacted by the Beowulf movement, because some of those dated all the way back to the 90s. And that's when everybody was experimenting with trying to build and learn from putting Linux commodity machines on Ethernet and treating that as a supercomputer.
What was your impression when you won the Gordon Bell Prize using a Beowulf cluster? And what did that tell you about the future?
At Supercomputing 97, Mike Warren, myself, and colleagues submitted 2 entries for the Gordon Bell Prize. And the simulation running on Beowulf clusters won the Gordon Bell Prize for price performance. After that, things really took off. Within 2 years, vendors were selling Beowulf machines instead of just calling them toys.
What role did open source and community play in the Beowulf cluster revolution?
In about 1998 or 1999, there was this community of Linux people getting together saying, hey, open source could be used to build supercomputers. And a small community started working on making Linux capable of being used for supercomputers. And it was a very exciting time in the open source community to believe that we could work together to build something that we could all share.
In 1994, version 1.0 of the Linux kernel came out. The creation of the Beowulf supercomputer brought a huge class of applications into the GNU Linux market, and it brought a lot of very good press to the GNU Linux community as more and more of the world's greatest supercomputers were running the same operating system. This created a great deal of very favorable publicity for the GNU Linux system.
As an early pioneer using commodity clustering, where did you see all this heading?
I think the open source systems and guidance we and many others developed over the years played a significant role in getting Linux clusters to where they are now. I also think the field has become too complacent with the technologies we have. We really need to be investing more in thinking about what's next. Of course, whatever people do invent, there's a good chance it'll still involve a cluster running Linux.
The Beowulf approach changed the course of HPC and replaced many more expensive systems with commodity hardware and open software. Beowulf clusters appeared everywhere, from PCs on wire shelves to servers in the data center. Users were no longer tied to monolithic supercomputers and could now design machines around problems, spaces, and budgets. Of the top 500 fastest computers of the world today, 437 systems are Linux-based clusters that owe their lineage to the original Beowulf project. How has the Beowulf cluster idea and principles influenced the top 500 list?
In those 30 years, Beowulf clusters have had a tremendous impact on scientific computing. If you take a look at the top 500 list, you'll see that 437 of the 500 systems are based on Beowulf clusters. It's the way we learn, experiment, design, and solve problems today.
With bigger and bigger clusters being created, is HPC out of reach for the average user?
Today, the Beowulf ethos is alive and well. From Raspberry Pi clusters to 3D printed cases, users have the ability to try new things in an open, vibrant, and collaborative community.
Where is all this headed?
As computing gets more fluid, so will HPC. New languages like Julia and HPC containers like Singularity are just 2 examples of how open access to the plumbing brings new capabilities to the market. And, as we have seen in the past, the Beowulf approach can quickly move new ideas and approaches to the forefront of HPC.
The Beowulf community and AMD have always been market movers in HPC. AMD has been and continues to be a supporter of open computing and recognizes the pioneering leadership found in the Beowulf community. Guy Ludden. Beowulf started as a new kind of high-performance cluster computer, one built from commodity hardware and openly available software, and grew into a philosophy that changed the technical computing landscape. The Beowulf concept ushered in a new level of performance and freedom where users can openly choose hardware, software, and even geometry by means of 3D printing as a means to accelerate their discovery. Communities supporting open ideas, best practices, software, and hardware came to life and accelerated the state of the art. Today, we have scalable, open, and efficient computing methods for science and engineering because our pioneers, thankfully, did not follow the rules. The next breakthrough is waiting.